All right, so no questions from last time? Yes.
Other question from my previous time.
No, it's not cumulative. So it's just now we're in chapter 9. It's just chapter 9 material. Final's cumulative. Yeah. Yeah. All right. So our next section is 9.5, the dot product. There it is. A dot. There you go. That's chapter. That's section 9.5. That's it. A dot dot times a dot. It's two dots. If it was only that easy, right? It is still easy though. To calculate the dot product given two vectors. If vector v is say ai, a1i plus b1j, and w, very similar. Let's put a2 times vector I plus b2 times vector j. The dot product of the two vectors is v dotted with w. We say dotted, not multiplied. It's similar, but it's not. Okay. You're gonna do a1 plus times b2. I'm sorry, a2. a1 multiplied to a2 plus b1 multiplied to b2. So just multiply the a components and add them to the product of the b components. And this is going to give us a scalar numerical value. So let's say vector v is equal to 2i minus 3j, and w is 5i plus 3j. V dotted with w. Again, always remember this is coming out to be a scalar quantity, not any vector anymore. It's a numerical value. Like when we did unit vectors, we figure out that we can divide by the magnitude. The magnitude was a scalar value, right? A real number. So this is just going to be 2 times the 5 added to the -3 times the +3. So it's 10 minus 9. The value is 1. So the value of that dot product is 1. Simple calculation, right? Keep that in mind. Very simple. Don't mix it up with something else that we're going to do later on, but you're not going to see that until next chapter. But this is simple arithmetic. Let's do, play part B. W dotted with V. Well, that's the 5 times the 2 plus the 3 times the -3. Still get the same thing, right? So dot products are commutative. Let's do the vector v dotted with itself. Right. So the a component multiplied to its a component again, plus the b component multiplied to its b component again. That's 4 plus 9. That's equal to 13. Let's calculate the magnitude. Remember, magnitude symbols that of v. So this isn't new. This is just still the square root of the a component squared plus the b component squared. So a is squared, that's 2 squared, plus b, negative 3 squared. That is the square root of 4 plus 9 is 13. So the radicand right here is the same thing as squaring the vector. So v dotted with v is the magnitude of v all squared, right? That's true. We square that, we square the radical disappears, both sides equal to 13. All right, so since the dot product is a real number, when we talk about vectors, we call these real number scalars. It's sometimes called the scalar product. So you might hear that term. We just saw some properties of this commutative property. We could do the dot product in any order. V dotted with W is the same as W dotted with V. We could distribute. Some vector U distributed over the sum of two vectors is the vector U. In a sense, multiply, but to multiply vectors, we do dot products. So it's vector U dotted with V plus the vector U dotted with W. So the vector U dotted with the sum of two other vectors. All right, so where do we use a dot product? Several places. One place is to find the angle between the vectors. So using the dot product to find the angle between two vectors. All right, so we're gonna come up with a formula, but let's derive it and see where it comes from. Instead of me just handing you a formula and you're like, okay, use it. You can understand where everything comes from. Memorizing it makes it a lot easier. All right, so we're gonna say let U and V be vectors with same initial point A. So if we draw that picture, let's see, this point A, and say it's going that direction. This is vector U, and this is vector V. And here's our angle we're looking for, call it theta. All right, so if I would say, if this is a vector right here between the two endpoints, I could represent this vector here as something. All right, here is V, right? I can also say that here is negative V, right? This picture is not coming out like I wanted it to be. Let's see. Let me draw this a little bit better to where it looks more like my notes instead of what I have here. I'm just going to extend vector V a little bit longer. I mean, it still works either way. It's just my scaling is not the best. There we go. Let's keep it like that. Vector V. All right, this right here would be U minus V. Take U, subtract off V like that. You'd have beginning to end. That's still not as good as I like it to be. That is U minus V. It's about like that. So beginning to end is U minus V right there. So we create a triangle. So we got a triangle of different lengths, right? Those lengths of magnitude for vectors U, V, and U minus V. Well, if I know the lengths of U and V, and I'm trying to find the angle between them, you remember some tree? Law of cosines? To find theta, use law of cosines. So this says the side opposite. Let's just put it in A, B's, and C's. You might be familiar with that if you remember. Let's say this is side A over here. So that would be A squared. This means this would be angle A. And these would be B and C, the U and the B. So A squared was equal to the B squared plus the C squared minus 2 times the product of B and C times the cosine of the angle associated with that side opposite of it. It's theta, in this case A. So that's just in terms of A, B's, and C's. All right, now let's rewrite it, what these A, B's, and C's are as vectors. All right, so this would be the side opposite of the angle right here, it's A. So that's U minus V. And we are looking for the magnitude, right, that represents the length of that side. So the magnitude of this squared, just for ease and clarity, I'm not going to put the little arrows on the top. It's going to get a little messy sometimes. The B is going to be this one right here, the magnitude of U squared plus C, the magnitude of V. I did put an arrow squared minus 2 times the magnitude of B, magnitude of U, that U, times the magnitude of V times the cosine of theta. All right, so this is the magnitude times the magnitude again. So really, I can just write it all out like this. U minus V dotted with another U minus V. It's vector U dotted with vector U, vector V dotted with vector V. Nothing to do over here. This is 2 times the magnitude of U times the magnitude of V times cosine of theta. Still with me? It's just simplification and substitution really right here. All right, let's do a side note and see what this is. All right, if I use the distributive property, basically, that's how you FOIL things out, really. I just want to do it that way, but I'm going to show one intermediate step. I'm going to say this u gets multiplied by all of this. So that's going to be u dotted with u minus v minus the v dotted with u minus v. Now you distribute across. That's u dotted with u minus u dotted with v minus u dotted with v again, or v dotted with u, it doesn't matter. Plus v dotted with v. So this is just nothing more than u dotted with u plus v dotted with v minus 2 u dotted with v. All right, so now we got to put all this back together. All right, so that's the left-hand side, right? You see some things cancel out, right? U dotted with u, same values on the left and the right, cancel them out. V dotted with v, cancels out. If I divide everything by -2 left over, the -2's go away. So we're left with u dotted with v is equal to the magnitude of u multiplied to the magnitude of v times the cosine of theta, divide by those two magnitudes, and you solve for cosine of theta. So now you just derive the formula to where the inverse cosine of this value, the product, the dot product of the vectors over the product of the magnitude of the vectors. That's equal to theta. So that's how I remember it, the dot product over the product of magnitudes. If you start trying to memorize letters and numbers and symbols and all that stuff, that can all get confusing. So you put it into words, it kind of helps you memorize things better. Yes? The magnet right here, the -2u, that was just from FOILing it out, really. First outer, inner, last. You need to multiply by the same binomial. Your outer and inner are the same exact thing, so you get two of them. So right here, you distribute it across right here. The second time was u times -v. It's -uv. And then -v times u. It's -vu, but we saw it as commutative. So you could say that's -uv as well. Okay, so you got two of those right there. A lot of times you put that term in the middle. I just put it at the end. Didn't matter. All right, so that is your formula. So find the angle between these two vectors. Vector u is equal to 4i minus 3j, and v is 2i plus 5j. All right, so we do the dot product. A component you multiply, 4 times 2, plus the product of the B components, -3 and 5. That gives 8 minus 15, -7. Next, the magnitude of U. So there'll be 3 calculations that you have to figure out what those values are. Then we're going to go into the calculator. So that's the square root of a squared, 4 squared, plus b squared, -3 squared. And that is 16 and 9, square root of 25, 5. Magnitude of v. 2 gets squared, plus 5 gets squared. That's 4 and 25. That's supposed to be a 25. There we go. Which is square root of 29. And that does not simplify. That's okay. It doesn't matter. It's all going to the calculator. Right? So we have that the inverse cosine of the dot product over the product of the magnitudes is equal to theta. Yeah. So that is not a value of a cosine of some angle that I'm familiar with, right? So you're not those special angles, 30 degrees, 60 degrees, 45, or any multiples of those. So yeah, we need a calculator for this. Let's express our answer in degrees. It's typically what it is. You talked about vectors. All right, so make sure you're in the right mode. I am in radian. Let's change to degree mode. And I hit inverse cosine, the second cosine button, and we have -7 divided by, put parentheses, because not it's just going to divide by the 5 and then multiply. We want to divide all by 5 square root of 29. And then close off the denominator. I can close off the argument if I want to. That's good. It doesn't matter for that second one. In the calculator, hit enter, and I have roughly 105 degrees. And this is where it's a really good idea to check. Just plot U and V. Everybody should kind of have an idea what 105 degrees looks like, right? 90 degrees is right. 105 is a little bit more than that. So it's an obtuse angle. So if I plot U and V, 4, -3, 1, 2, 3, 4, 1, 2, 3. In standard position, position vector, this is U. V2, then up 5, 1, 2, 3, 4, 5. That does look to be correct, right? So if I would have got something that said like 45 degrees, and if I had drawn that, I was like, well, something's off. I did some error in my calculation somewhere, so you can see how quickly it is just to plot that and make sure it looks correct. Or you just break out your protractor that you carry around with you in your back pocket every day. You can actually just physically measure it, right? All right, parallel vectors. Let's say if V is 3i minus j and W is 6i minus 2j. Let's just plot them and we can definitely see. I'm going to plot them separately, not on the same axis because they're going to overlap each other. So 3, 1, 2, 3, -1. 6 and -2. 1, 2, 3, 4, 5, 6. Down 2. So you can obviously see if you move these things around, they stay in the same position and their lengths, right? But you can put them right next to each other and they are parallel, right? Just graphically. Now, you can't prove things graphically, right? I don't know if that line might be slightly tilted more and then eventually they may intersect, right? So algebraically, to prove this, we're going to do this using the dot product. So if the dot product of V and W equals 0, then this proves G and W are parallel. So let's got the two vectors, 3 times 6 plus -1 times -2. I'm sorry, I said it's the dot product if the angle, excuse me. We use the dot product to figure out the angle. If the angle of V and W is 0 degrees, right? I mean, if there's no angle between the two, that's it. Then this proves V and W are parallel. So we calculate the dot product first, right? So that's 18 plus 2 is 20. Magnitude of V is 3 squared plus -1 squared. That's square root of 10. Magnitude of W, square root of 6 squared plus -2 squared. That's 36 plus 4 makes 40, square root of 40. Again, you don't need to simplify these. Square root of 40, you don't have to say that's 2 square roots of 10. If you want to, that's fine. But it's all going into the calculator anyway, perhaps. So the inverse cosine of the dot product, 20, over the product of the magnitude, square root of 10 times square root of 40. That will be equal to theta. Or actually, from here, I could do this without a calculator. Because this comes out to be some nice numbers. So this is cosine, inverse cosine of 20 over the square root of 10 times 40 is the square root of 400, which is 20. This says the inverse cosine of 1 is equal to theta. Who has a cosine value equal to 1? Right here, right? 0 degrees. Remember on the unit circle, this is 1 comma 0. 1 is the cosine of 0 right there. So theta is equal to 0 degrees. So therefore, V and W are parallel. All right, another similar concept of parallel is something called orthogonal. And so they're not running side by side, but they do intersect, and they intersect at a special angle that is 90 degrees. So orthogonal vectors they intersect at a right angle. This is where when you find the intersection of the two vectors and the angle between them is equal to 90 degrees, right? So what is the cosine of 90 degrees? That's equal to 0. All right, so remember the order pair is 0, 1 to get to that point on 90 degrees, right? So if we do the dot product, is equal to 0, then we can have something in the format the inverse cosine of 0 divided by whatever numbers these come out to be, it doesn't matter, equals theta. This is still the cosine, inverse cosine of 0 is theta, so therefore theta is equal to 90 degrees. So all you'd have to do for these, you can go through the whole process, but if you get your dot product to be 0, that means you have orthogonal vectors. All right. So let's just do an example real quick. Again, you can plot these, but again, graphically, you can't prove it. That's 2 times 3 plus -1 times 6. That's 6 minus 6 is 0. Really don't even care what the magnitude of V is. But that's 2 squared plus 3 plus -1 squared. I'm looking at the wrong one. That's 4 and 1 makes 5, square root of 5. And W, I really don't care about it because this is my numerator, 0 divided by anything. It's still going to be 0. 3 squared plus 6 squared. 9 and 36 is 45. So now I have the inverse cosine of 0 divided by those two radicals. It's still the inverse cosine of 0, which is theta, 90 degrees. And if you still don't believe me, use a calculator, right? Second inverse cosine of 0 equals 90. So it's the right angle between the two. So know when you get to Calc 3, you use a lot more of this stuff when you're trying to find orthogonal points or lines in 3 dimensions. I remember doing something like that. I've got a line going this way in space and a line going that way in space. When they intersect, will they come at a perfect right angle? Even planes. All right. All right, so we know how to do vector addition, right? And subtraction geometrically. Okay. So adding 2 vectors gives the resultant vector, right? So let's just say I had vector V, vector W, vector V plus W geometrically would be that, tack on W, this, and the result would be that. So now we can go backwards. Suppose I give you the resulting vector And I want to know what were two other forces or something of that sort that created it to go in that general direction. If I can give me one vector, figure that one out, and I can figure out the orthogonal vector to that one. Okay? And then the sum of those two orthogonal vectors would be this resultant vector. So we're going to go backwards, and that's called vector decomposition. All right, so let's suppose vector v and w. Let me see, not plus w. Let me say word and. Are two non-zero vectors. It's just math jargon, right? So the vectors, they have length and magnitude and direction with some initial point. I'll try to draw this as best as I can. Let's say, so here is V. Let's put a different color for W. We're going to decompose V into two vectors. We're going to call one V sub 1. This is going to be parallel to W. So it's going to look just like W, but of different length. It may be the same length, I doubt it, but it's going to be either shorter or longer than W. And then V2. Once we find V1, we're going to find V2 to be orthogonal to V1. So V1 is called the vector projection of V onto W. So this would be V1. Let's put this in purple. That's V1, which is the vector projection of V onto W. And then orthogonal to V1 is V2. Now, I don't know how long these lines are with those vectors that are drawn. They could not be this long. It might be really short. It might be much longer. I don't know. But that's the concept. So this is V2. All right, so to get V2, if I take the vector V, which is like that, perhaps, and I subtract off V1, the opposite direction, like that, from beginning to end would be V2, right? So that's how you get your orthogonal one. The original vector minus the V1 that you just found. All right, so let's figure out how we're gonna initially figure out what is V1. All right, so V is formed by V1 plus V2, right? I already said V1 is parallel to W. And V2 is orthogonal to W. Remember that notation for parallel and two angles orthogonal or form a right angle. Two vectors are form a right angle between them with that notation. Yeah. Right here. That's just two vertical lines supposed to be parallel. That's parallel. No, you know I can't draw straight lines. There we go. It's not bad, right then. All right, so now we have a formula. Okay. So if V equals V1 plus V2, then dot product. Yeah, is that green okay? You can see that? Okay. V dotted with W is equal to, just replace what V is, V1 plus V2, right? Just making this substitution. Dotted with W. W can be distributed across. And since V2 is orthogonal to W, that means the dot product of V2 and W equals zero, right? So this is zero right there. And since V1 is parallel to W, V1 is just some scalar multiple of V of W. So I put an alpha right there. Alpha means a scalar multiple. So some number multiplied to W. So that number, it may be like a fractional value which shrinks W, or it might be a bigger value that gets multiplied to W to make it larger. So this is for some scalar alpha. So now we can replace over here, V dotted with W is this V1 dotted with W, excuse me. V1 dotted with W. Here's V1 alpha dotted with W. is V1, dotted with W. So that's V1, all right? So W dotted with W, that is the magnitude of W squared, right? We saw that one earlier too, if you recall that. So this is alpha as the magnitude of W squared. If we solve this for alpha, so alpha is V1 dotted with W at V1. Hold on. Okay, yeah. I don't know why I solved for alpha there. It's kind of going in circles, but that's okay. Then V1 is, we saw alpha times W, right? So there is alpha, which I don't know why I got V1 right here. It's supposed to not be a V. It's just vector V dotted with vector W all over the magnitude of W squared times the vector W. All right, so we got a formula for V1 now. The product of the vectors, dot product of the two vectors, over the magnitude of vector W squared times the vector W. And then V2, we saw it was the original vector minus V1. All right, so let's find the vector projection of V, which equals just I plus 3J onto W, which equals I plus J. All right, so let's calculate what V1 would be. So dot product over the magnitude of W, one that's being projected squared, times W, projected on 2. So V dotted with W, let's say 1 as a coefficient in front of that I, so it's 1. Same for W, So that's your A components, 1 times 1 plus B components multiplied 3 times 1. That's your numerator. The magnitude really can ignore the squared because then you just take the radical away. So you're just looking at W, right? But we need a constant. That's why we take the square root to give us a constant and we square it. All right, so W is going to be the magnitude of W, that is 1 squared plus 1 squared is 2, square root of 2 on the bottom. All right, so that's 1 plus 3 on the top is 4 over the square root of 2 all squared times W. I'll write in what W is in a second, but we're just trying to get the scalar right now. So that just gives us 2 in the denominator, right? 4 divided by 2 is 2 times W, and 2 times W is going to be 2 times I plus J. So V1 is 2I plus 2J. V2, that's the easy one now, is the vector V minus V1. The vector V was I plus 3J. Minus the vector we just found, so minus all of it, so we'll have to distribute a negative across the parentheses. So I plus 3J minus 2I minus 2J. Combine the like terms. 1I minus 2I is negative I. 3J minus 2J is plus 1J. All right, so we can check this. I'm going to plot V and W, V1 and V2, and see how they are related. V1 and V2 better be orthogonal to each other. V1 better be parallel or lined up onto W. So let's go here. All right, V was I plus 3J, so 1 over 3 up, right? So I'm going to make this kind of large so it's easy to see. That's V. W is I plus J, so 1, comma 1. Put it in blue. So I want V to kind of like lay down onto W and then open W back up to another vector that's going to be perpendicular to it. So that's why V is going down onto W, but it's going to be a different length. So V1 is 2I plus 2J, so that's 2, comma 2, right? So there is V1. And then we do V2, negative I plus J, that's negative 1. Positive 1. And that is perpendicular, right? Looks perpendicular. So we should be having the correct vectors. Questions? So it's just really a couple formulas I've given you, and it took me an hour to talk about all that, huh? Like, why you couldn't just give me the formulas and just do a problem, right? We're in here for a while, so I gotta extend the time and bore you out, right? All right, y'all like word problems, right? Real world examples. Let's finding the force to hold a wagon on a hill. All right, two kids are in a wagon with the total weight of 100 pounds. Make the numbers easy. So the wagon plus the two kids is 100 pounds. They're on a hill with a 20-degree grade. What magnitude of force is required to hold the wagon so it doesn't roll down the hill? All right, so there's our hill, 20% grade. And of course, we have to draw pictures. Get our wagon. Get our two kids in the wagon. All right. Think they're scared. Because whoever's holding the wagon might not be strong enough to hold them up, right? And let them go. And, ah! All right, so we got some vectors in here, right? So let's do, we know one of them, the weight, definitely, right? So weight projects straight down due to gravity, right? So from here, straight on down, is a force vector, let's say F sub W for the weight. And we know I can write this as, if it's going down, that means going down exactly vertically, that's following the J axis or whatever, J component, right? But going down means negative, right? So this is negative, how much is the magnitude? 100 J. So that can be written as 0, comma, negative 100. You want to put it that way, right? AI plus BJ is A component 0, the B component is negative 100. Now we have this vector. Now think about it, if you let it go, that's how much force is going to go down. So you need the opposite force, right? So the magnitude of those two vectors are the same, right? It's going to go how much force. If I need 30 pounds of force this way, if I let it go, it's 30 pounds of force that way. So we're looking at just this vector right here. And whatever arrow you want to put on it, doesn't matter. I'll say it like that. If we let them go, they're going to go down. Let's call that one vector B. So in the opposite direction, right here, this vector that's going uphill in a sense, right? I can represent that vector. Let's call that one W. So vector W, I can write it in terms of its magnitude and its direction. I have its magnitude. I have its direction, right? So I know that vector W, let's see, this was f of W. Vector W can be written as the cosine of 20 degrees times vector I plus the sine of 20 degrees times vector J. Now, if I can get the vector projection of this onto W, I'll be able to calculate how much force is needed. So we've got V1 that's going to go onto W. It's going to be the dot product of f of W and W divided by the magnitude of what you're projecting onto, W, all squared, times W. All right, so this gets a little bit messy because we don't have actual specific numbers we're dealing with, but we got these two right here we can work with. All right, so here's my A, here's my B, here's my A, and here's my B. So this is 0 times the cosine of 20. Plus negative 100 times the sine of 20. All over the square root of cosine of 20 degrees all squared, or cosine squared 20 degrees, plus sine of 20 degrees all squared, or sine squared of 20 degrees, multiply 2W, which is cosine 20 degrees times vector I plus sine 20 degrees vector J. All right, you can see how all this is going to simplify up. All right, 0 times anything still 0, right? Let's look at the bottom. Cosine squared of something plus sine squared of something, that totals 1. Not a negative 1, positive 1. Square root of 1 is 1. So what's left over is just negative 100 sine 20 degrees times the cosine of 20 degrees I plus sine 20 degrees J. All right, this represents your V1, which is parallel to W. So let's figure out what negative 100 sine of 20 degrees, that's going to be our magnitude, right? Remember R times, or let's see, in this case, it was the magnitude of the vector times its position, cosine of vector I, whatever the angle was, plus sine of the angle J, right? So this is our magnitude. of V1. So that's the amount of force. Calculator, negative 100 times the sine of 20 degrees. And that's negative 34.2 pounds of force. So that just means to overcome that force that's pushing it down, I need to pull it the other way around to be zero so it doesn't move at all, right? So if I exert a force of more than 34.2, then I'm moving uphill, right? If I let it go. All right, so this will keep it from moving at all. So absolute value of that, I should say, right? So 34.2 pounds keeps it stable. All right, that is the hardest thing there is in this section, but kind of can get an idea. There's not going to be a whole lot of problems in my math lab that's going to be much different than what's here. It might be different words. You have a piano or something that's going up a hill or something, or how much force it takes, same kind of situation. So you know you're dealing with vector projections. All right.